Hey everyone, I'm Pooja Trivedi. I'm an architect leading developer experiences in AI for Linux on Windows. And I'm joined here today by...
Hi, my name is Craig. I'm a product manager working on the Windows Subsystem for Linux and other awesome AI tools on Windows. And today we're going to be talking to you about a new feature, WSL Containers. And so really the talk boils down to just these 3 points. So this is the only really 3 takeaways you need. The first is you're going to be able to run Linux containers locally on Windows. That includes running them directly, part of a CLI, or running them as part of an API within Windows applications. Second is that it's going to be part of the Windows Subsystem for Linux. So this will just be a new feature that you get directly as part of WSL. No need to install something new. It will just be part of an existing package that I hope you're already using. And the third is that we want to make this enterprise ready. So this means that all the industry standard tools that you're using, like MDE, Intune, and more, all of that will just work with WSL containers as well, so that you can feel secure and safe using this inside of your enterprise environment. And I think really the fun part here is let's go and jump out of the slides and jump into a live demo of taking a look at the CLI. And so if we could switch to the other machine, we'll take a look.
All right. As Craig said, when we ship this, you will get the full capabilities of WSL containers via a simple WSL update. You don't need to download any third-party tools, no starting of daemons, no Faustian rituals. And what it comes with is a command line tool called...
You can't switch? Okay.
Can't switch?
Oh, great. Oh, it switched.
OK.
Nice.
What it comes with is a command line tool called WSL-C. And here I wanted to show you the command reference that the tool exposes. And as you look at this, you'll realize that it looks very familiar to you if you're used to using any of the standard Linux container tools out there. All the subcommands, options, switches within these also track very closely. We've also internally aliased it to container. So if you're more familiar to using container, you can use that binary. Let me start by showing you a really simple flow here. I'm going to start by showing you how to create a Debian Linux container on Windows. And if you're not familiar, the -IT switch here tells WSL-C to give me an interactive shell into my Debian Linux container. Normally, it would download this image for me from a public registry if I don't have it here. We have some internet issues here, so I pre-downloaded it. And so I'm inside of the shell of the Debian Linux container. I can detach out of it using the standard Control-P, Control-Q sequence. And now, if I do a WSL-C PS-A, or if I do a WSL-C container list, if that's more familiar.
Container list.
Container list. You'll see that the Debian Linux container started about 40 seconds ago. I'm going to attach back to my container using WSL-C attach and the container ID or the container name. And there it is. I'm back inside of Debian Linux. I'm going to exit out of this container and terminate it. And WSL-C PS-A will now show me that the Debian Linux container is exited about 4 seconds ago. So this was a really simple flow. Next, I want to show you how you would build custom images using WSL-C. You would want to use this when you want to bring your cloud workloads or your production workloads directly onto your primary Windows development box so that you can iterate on it, test it, debug it locally. And that way, because it's packaged as a container, you get the same environment that you have in production locally on your box here. And so you don't have the gotchas of it works in dev, doesn't work in prod. So let me start by showing you a container file. If you're not familiar with this file, the container file has all the ingredients and the recipe that you need in order to build your container images. So it packages up your environment, your dependencies, your application logic, the instructions on how to run your application into a file. And then you can use this to build a container image. For me here, it's a really simple Linux utility I wrote for fun, which allows me to run all of my favorite Linux inspection commands on any file I drop to it. So the first line here is basically saying that my container environment starts with a very simple, lightweight Python 3.12 image. The next few lines here are installing all the dependencies that are needed for my container and my application logic to run successfully. Here I'm copying my application logic into the container. And it's a web server that listens on port 5000. So I want to expose that port out of my container and map it onto my Windows box when I run this container so that I can interact with this web server that's running inside of the Linux container locally from my Windows box using localhost. And then the last line here is the instructions on how my application should be started within this environment. So let me build this image using WSLC build. I'm going to call it my Linux spy. And I can use the container file to build this. There it goes. And now if I do a WSLC images, and yes, you can use grep here on PowerShell because I'm going to do a shameless plug here for another friend of mine. We have imported all the core utils, about 168 Linux utils into Windows now, which are fully integrated. So here's the image that just built. It says 9 hours ago because some of the caching for base layers was already used. I'm going to now start a container using this image, and I'm going to do a port mapping. As I mentioned earlier, my container web server listens on port 5000. I'm going to map it to my Windows host using this -p switch. And here I'm starting up my container. And there it goes. I can now hit it on 127.0.0.1, which is localhost. And I can interact with my Linux spy, my forensics tool here. And there it is. It runs all of my favorite Linux commands on it. So now that I've shown you how you would expose services out of a Linux container onto your Windows host, I wanted to show you something more interesting. I wanted to show you how these containers can actually tap into the GPU that's present on your Windows host for your AI scenarios, or if you want to run graphical applications or whatever have you. I've already built my container and pre-warmed it, so it's already running. I did that to save time. And I'm going to start. It's a Jupyter Notebook web server. Again, it listens on port 8888, which I exposed out using port mapping. I'm going to start running these cells while I tell you what this cool AI container of mine does. What it does is it actually pulls down a GPT-2 model, and then it fine-tunes it on the GPU on this Windows host. And then it torch compiles this so that it generates fused Triton kernels. Those fused Triton kernels are optimized kernels that allow my model to run really fast on the GPU. And then for your entertainment, it shows you a head-to-head race between a compiled model and its uncompiled eager mode counterpart. And you can see how fast the compiled model runs. And while all this is happening, the GPU on my Windows box here is being leveraged to do all of this work inside of the Linux container. And before I hand it back over to Craig for some more WSL containers goodness and how you can embed those into your Windows application flows, I quickly wanted to show you the command that I ran to start my AI container here. So I ran it using run-it. You're familiar with that. I showed you earlier. There's port mapping. And then the -v switch here is saying that I want to mount volumes. So I want to mount the the Hugging Face cache directory that's on my Windows host here onto this location into my container. And then the --GPUs all switch is asking the Linux container to use the GPU on my Windows box here. And I'm going to hand it back to Craig.
Awesome. So if we jump back to the slides, we'll be able to see kind of the next step. And really, the summary of that demo is there's two ways to interact with WSL Container. There's the CLI, which Pooja showed as an awesome way to directly interact with those containers. But we also have an API. So the CLI is perfect for direct container access, direct building, running. And then the API is going to be a NuGet package that you'll be able to run. And it's basically two different doors for the same engine. It's all powered by the same WSL VM that actually powers WSL distributions. And really, when we talk about this, it begs the question, why did we build this? Who is this for? What are our goals at Microsoft for making this technology? And that breaks down to three different customer profiles. The first is, if you're a container developer, this is for you. If you like to build, use containers, We wanted to make it easier to get started with, to use containers, and have that all run seamlessly on Windows. We also wanted to be able to be opinionated about our approach. We know that we were building both an API and a CLI. So we want them to work together, and we're probably going to write some pretty custom commands to do that. That's why we built our own Linux Container CLI, as opposed to using other standard tools like Docker or Podman or Rancher Desktop. However, those tools all work great, and if they still solve problems for you, you should use them. This is just another approach. And by nature of this work, this is fully open sourced. It's fully open sourced on WSL, and all of the code that we're doing, all the improvements that we're doing to the underlying VM technology are going to accrue to those other container technologies as well. So for example, we're improving the cross-OS file performance. You'll get that as well on Docker Desktop, Rancher Desktop, Podman Desktop, as well as on the Linux Container CLI inside of WSL. Secondly, we're also wanting to build this for app builders and ISVs. We want you to be able to take some awesome Linux code that you have lying around or in the cloud and run that directly and locally as part of a Windows application. We want you to be able to do that all using really standard and powerful APIs in your Windows app. And lastly, we also are building this for enterprise IT admins. These are folks who, hey, I want to run OpenClaw inside of my enterprise, and I want to run that in a containerized environment using Linux, but I want to manage that using all the Windows tools like Intune or MDE that I'm familiar with. We're building this exactly for scenarios like that, where I want to be able to use these powerful tools and applications and run Linux on Windows, and I don't want to be afraid of, hey, there's a black box, opaque VM running in my organization. How do I access that? I want to make sure that you get that powerful isolation without having to worry about your security tools not being able to break that boundary. And so this brings us to a really awesome plug that we wanted to show for one of the partners that we've worked with. We have worked a lot with the Moonray team. Moonray is a very powerful rendering engine that is used to render amazing movies like The Bad Guys 2 or The Wild Robot, which I'm a big fan of personally. And that rendering engine is built entirely on Linux. And so we've been able to work with the Moonray team to say, hey, how could we make it easier to get started with Moonray, which is also an open source application, and be able to use that on Windows. And so that brings us to our second demo of let's go ahead and run the API portion of WSL Containers. So I'm going to flip over here, and you can see I'm in this project, and I'm about to go run Moonray.exe, which is a build that I've created. So again, this is a full Linux-based rendering engine, but I have an exe on my system, and then I've given it some files. Of course, it's backslashes, so we're running this in Windows, and I've given it some input RDLB, which are just render input files, and then I'm saying, please output this JPEG for me. And I'm going to open up Task Manager so we can take a look at what's happening while we run this. When I run it, I've left some debug info here. It's starting up a session for me. That's how quickly it started the container, and then now it's doing the full render. And so if I look at my CPU, all of the render is happening on my CPU. It's happening directly inside of this Moonray VM right here. And then now that the render is complete, the Moonray VM shuts down, and all of that gets released back to Windows. So it's totally seamless. If I did not include these debug messages, it would just look like a Windows app. I would actually be none the wiser that this was running Linux in the back end. And then the cool part is if we take a look at the output, you can see it outputted that JPEG for me right here, which is a wonderful orange coffee maker showing some of the cool rendering of see-through ray tracing applications there.
So this VM creation in the background, all of this running is all completely transparent to the user of the API. All you're doing is you're creating and managing containers via the API.
Exactly. So you as the developer can have control. Hey, I want some Linux code, but I don't want my users to ever worry, am I running Linux or Windows? It just should all just work. So let's take a look at a sample project that's related to see how this might look in a code perspective. I have some container or some NuGet packages. I added this containers package, and then I've defined this item group here saying, please build this container for me. You can find the container file here and output it here. And if you take a look on my left-hand navigation, that container file is directly with all of the source code of my app. It's built into my application.
So this is all a part of your CS proj file. So
Exactly.
the container file as well, so it's all integrated together as a single experience, even
Exactly. And when I build and run this, it will automatically build the container for me, so one F5 experience, and then it's going to run my sample app. In this case, this app is a fake and very whimsical app that I built. I wanted to build an AI agent that would run stocks for me, so it's going to buy and sell some fake stocks. And that's the container starting up. It's starting a bunch of processes and services in the background, and then now it's started my stock trading. And so I've hired an AI agent I called Herbert to buy and sell some stocks. And what actually is happening is I've given this container its own desktop, and I've given it a visualization of the desktop so we can see what's happening. And we can see the AI agent actually goes in and makes some fake stock trades, but he has a really bad habit of eating files. So yes, I actually did program this to go randomly delete files on my system. And when it deletes a file, it really deletes it on Windows. So that actually deleted the file here. And what we're highlighting is that there is a high level of integration between the container and Windows. You can specify, I want these ports open. That's how I viewed that desktop that I showed. And you can specify, I only want it to access this file on Windows. So I minimize the blast radius. Even though it really was deleting random things, I'm okay with showing that on this demo machine because it could not physically delete all the files on Windows. It could only delete the files in this ctemp Herbert folder. So that's a very quick overview of where we're going with the API. And I'm sure the next burning question that you must have is, how does this all work? So Pooja, would you be able to explain some of the architecture?
Yeah, sure. So the way this works is every Windows application intending to create Linux containers gets a lightweight utility VM that's dedicated to it, that's created in the background. All of the application's Linux containers are co-located on this VM. Every application, as well as the CLI flow, gets a separate VM. And what this gives us is a hypervisor boundary per app, and it also gives us resource separation and a way to not cause conflict. So all of a container, an application's containers, its names, its volume names, networks are all isolated on a VM basis, so there is no conflict there. Going into a little bit more detail, on the left here, you see the Windows operating system, and on the right is a virtual machine that was either created by a Windows application, by calling into the WSL Containers API, or the CLI flow. So as we mentioned, the two entry points into the WSL Containers world are via the API, which is exposed by a library called WSLC SDK. We publish it via a NuGet package that Windows applications can include and then start interacting with the WSL Containers API to create and manage containers. Or the other entry point into this world is the WSLC command line executable or container executable that I demoed earlier. Both of these talk to WSL service via inter-process communication. If you've used WSL service exists today. In that world, it is its job is to manage the distros that WSL runs, the life cycle of the WSL virtual machine, and the communication between the VM and the host. We've augmented this same service to now manage the containers that run within these VMs. And it also manages and relays information back and forth between these containers and the users on the Windows host side. Inside of the Linux virtual machine, we run a container runtime. Today we run Moby. It's an open source engine that powers Docker today. And WSL service uses an HV socket to communicate users' intent to the container runtime by opening this HV socket with the Linux virtual machine. It is not a network socket. It's a specialized socket that is used specifically for communication between the VM and the hypervisor. It's a special extension of the WinSock API. And every VM it's sort of like a point-to-point per VM to the hypervisor. So it's an isolated communication channel for every VM. And once the user issues a command for container creation, the container runtime goes ahead and creates those containers, and WSL service does the job of relaying that information back and forth. Sorry. Oops. Excuse me. So that's that. Next, I wanted to quickly touch on storage. The container runtime inside of every virtual machine uses a central directory within this VM to store container-related information. It's metadata, it's scratch space, etc. And usually it's a location like var_lib and the container storage location. What we do is we now map this location onto a virtual disk on the Windows host side or a VHD. And every application gets its own VHD as well. The CLI flow also gets its own VHD. So at the storage level, everything is separated per application as well. And lastly, I quickly wanted to show you what the flow would look like when a command, as shown above, is run. The run-it, I've already talked about before. The volume mount here is saying that I want to map my /data directory on the Windows side onto the /data mount on the Linux containers side. And I want to create a Debian latest container. So when this is issued, the container runtime creates that Debian latest container, and then it attaches a /data volume onto this container. And then under the hood, we go ahead and map this /data folder or volume onto the /data folder on the Windows side using virt.io/fs. virt.io/fs is a relatively new file sharing protocol that is used for sharing files between VM and hypervisor. And for us, we have this added complexity here of translating all of the file system semantics between two completely different operating systems. If you've used WSL, it uses Plan 9 today. virt.io/fs is about twice as fast as it stands today in this environment, and we're investing more in these areas and looking at various alternatives as well to make this even faster. And before we wrap up WSL containers here, I wanted to also quickly take a detour and mention what else is new for WSL. Microsoft's Linux distro, Azure Linux 4.0, is now available for general use, so that's exciting. It is the same distro that runs AKS today. This is what powers Azure, so if you use this, it gives you a consistent, battle-tested, proven environment. Microsoft provides the entire stack for Linux. So it's a single vendor, full supply chain attestation from build to deployment, so you know where to go if you have issues. It's available today for VMs, so you can try that out. And the WSL distro is coming out soon as well. So once that comes out, we would love for you to try that out as one of the distros for WSL. It is container optimized. It is lightweight. So please try it out and let us know what you think. And that's it for WSL containers. We will be posting on the CLI blog when this goes live. Please try this out with your real-world scenarios. Let us know. Give us feedback so we can improve.
And we plan to have this go public preview by the end of June. So you will be able to try it out there. We're open source, so you can go check our progress at Microsoft/WSL. And then we'll be here for questions, as well as the dev lead for Moonray will be here as well, if you have questions. So thank you very much. Thank you all.